Hello everybody and welcome back. We're going to continue on looking at the 2012 Friar contest in this video. We're going to be looking at question number 2. We just did question number 1, so if that's what you're looking for, go back. It's the previous video. And yeah, so let's take a look at question number 2 now. Alright, the prime factorization of 144 is 2 times 2 times 2 times 2 times 3 times 3, or 2 to the 4 times 3 squared. All right, we have 4 2's, so that becomes 2 to the 4. We have 2 3's, so that becomes 3 to the power of 2, also known as 3 squared. Therefore, 144 is a perfect square because it can be written as in the form 2 squared times 3 times 2 squared times 3. So 12 times 12 gives us 144. So the easiest way to see a square in terms of its prime factorization is if all the exponents are even, we get a perfect square. If they're not, we're lacking a little bit. The prime factorization of 45 is 3 squared times 5. Therefore, 45 is not a perfect square. Notice it doesn't have an even exponent over the 5. But 45 times 5 is a perfect square because 45 times 5 works out to be 3 squared times 5 squared. So we can split that up into 3 times 5 times 3 times 5. And indeed, if we check it out on our calculator, 45 times 5 is 225, which is 15 squared, just as they predicted. Alright, so that was a bit of a preamble. Now let's jump into the actual question portions of question 2. So A is a light bulb question. Determine the prime factorization of 112. Okay. Well, there's not a whole lot to do. We just need to split off primes as we go. So there's not a whole lot of explanation we can write. We're just going to actually write down the values. Okay, so 112. I noticed that this is even, so most of my prime factorization will be me describing it and not writing it down. I notice this is even, so I can split off a factor of 2. And you can work it out on your calculator or do it in your head. You get 2 times 56. So 2 is a prime number, so we're going to include that in our prime factorization, but 56 is not. It's got another factor of 2. How do I know? Well, it ends in a 6. 6 is an even number, so this has 56 is divisible by 2. I get 2 times 28. Okay, well, 28 is also even, so we can split off another factor of 2 and left with 2 times 14. And 14, we can really quickly get its prime factorization. 2 times 7. 7's a prime, so we stop our process. But we want to collect these guys up together, so 2 to the 4. We have 4 2's times 7. And we could write 7 to the 1 if we wanted to. Notice again, as I was saying, this is not a perfect square because we have 7 to an odd power, so if we have any odd exponent, we're not looking at a perfect square. But we can double check this by saying 2 to the 4 is 16 times 7, and that is indeed 112, so we have definitely done the proper calculation. Alright, so we would write 2 to the 4 times 7, or 7 to the 1 if we were feeling sassy, into the box provided. So B part. The product 112 times u is a perfect square. If u is a positive integer, what is the smallest possible value of u? Okay. So let's write down the rule I've been using. Alright, so if we're looking at a prime factorization, we get that the number that we're looking at is a square if and only if each of the exponents is even. Okay? So we want to get a perfect square out of this, and we want to make u as small as possible. So if we want to turn 112 into a perfect square, we need to, at the bare minimum, make each of its odd exponents so we need to take each one of the odd exponents so we just need to multiply it by 7 and we'll get a perfect square. Anything less than a 7 is not going to give us a perfect square. Any more 2's is not going to help. We just need at least one 7 to make 7 to the 1 into 7 squared, which is an even exponent. So all we need to do is take u to be equal to 7. Alright, so now we need some written style parts of the question. C. The product 5,632 times v is a perfect square. If v is a positive integer, what is the smallest possible value of v? Okay. So just like in B part, we're going to need to figure out the prime factorization of 5,632 and then figure out what we need to add to it and to make all the exponents even. So let's first factor 5,632. Well, I know it's going to have a 2. As a matter of fact, I know it's going to have a 4, at the very least. Yeah, it's definitely going to have a 4, so we're going to write 4 times 1408. Actually, yeah, well, I guess we could have had an 8 here. That's 2 to the square, 2 squared, so 2 to the 2. And then we have another factor of 2 here. Get 704. Another factor of 2 here. In fact, actually, we get a factor of 4 here, because it ends in a multiple of 4. We're left with 176. Okay. So now we're looking at 2 to the 5. I have another factor of 2 here. Actually, it's another factor of 4. 76 is 4 times 19. So that's 44. And at that point, we can easily get 2 squared times 11 here. So that's 2 to the 9 times 11 to the power of 1, I guess. And we can double check that. Yeah. 2 to the power of 9, that's going to be 512 times 11, that's 5632. Okay. So we need to make these odd exponents even. So we have a 2 to the 9, that's odd, and we have 11 to the 1, that's odd. So we need to have at least a factor of 2 and at least a factor of 11. And I don't care what else we have, but just that, that's the bare minimum to make the exponents even. But we want v to be as small as possible, so we don't have any other bells and whistles. We just have v have to have that factor of 2 and 11. So v is going to be 22. I guess we could have a little therefore statement. Therefore, v is 22. Okay. So that's C part. Knowing that we have to make the exponents even is a great help. Alright, D part. A perfect cube is an integer that can be written in the form n to the power of 3, where n is an integer. For example, 8 is a perfect cube since 8 is 2 to the power of 3. The product 112 times w is a perfect cube. If w is a positive integer, what is the smallest possible value for w? Okay, so we're back to using 112. Now, fortunately, we have its prime factorization. But to get a perfect square, we needed even exponents. We can modify this rule to get perfect cubes. I'll show you what I mean. So we get a perfect cube if and only if 3 divides each of the exponents. Each of the exponents is a multiple of 3. Why does that work? Well, let's say that they're 3 times something. Let's say they're 3 times di. Well, then we can replace the EIs with these 3 DIs. But we can take out an exponent of 3 and bring that outside the brackets. And this proof goes both ways. If we start with a perfect cube, we know n looks something like this. So factor what it's the cube of, prime factorize what it's the cube of, and we bring this 3 in, we get a prime factorization of n, and each of the exponents has a multiple of 3. If we start with n, and each exponent has a multiple of 3, we can bring that 3 outside the brackets, and we get an integer in here to the power of 3, gives us n. And you can generalize this rule for any power. So if you want 4th powers, each exponent's got to be a multiple of 4. You want 5th powers, each exponent's got to be a multiple of 5. This is sort of basic prime factorization stuff. Do they expect you to know it? Not exactly, because, well, as they point out, if they expected you to know what prime factorization was, they wouldn't introduce it at the start of the question. However, this sort of extra knowledge definitely helps us. And now if you see prime factorizations on a contest, you might start thinking like this. But it's given the information they had, this sort of setup is naturally something that we can conclude. We could conclude that you need even exponents to get the perfect square just from the examples they gave us in the question. So now we have our new perfect cube rule. 112 times w, well, that's 2 to the 4 times 7 to the 1 times w. So in order to get exponents that are multiples of 3, we have to at least have factors of 2 to the 2 and 7 to the 2. Why? Well, 2 to the 4, that's not a multiple of 3 by himself, and we can't subtract anything. We can't go down to 2 to the 3, so we have to go to the next multiple, which is 2 to the 6. Don't know why I can't seem to write a 7 right now. Now, 7 to the 1, that's not an exponent that's a multiple of 3, so we need to add 2 to it to get 7 to the 3, which is a multiple of 3. So 2 squared times 7 squared should do the trick. Well, that's 14 squared. That's 196, and if we check, we multiply that by 112. That is indeed a cube. And what cube is it? Well, it's going to be 28 cubed, I believe. Yep, exactly 28 cubed. All right. So we explained our reasoning. We set up our criteria to get a perfect cube in terms of prime factorizations. And we just took W. We figured out the minimum requirements. What does W have to complete 112? 112 is part of the way there to a cube. But what else does the prime factorization of 112 need to get to a perfect cube? And those are the minimum requirements on W. We want W as small as possible, so we don't add in a 2 to the cubed or a 3 to the cubed with W. We just take it with what it needs, which is a 2 squared and a 7 squared. So W must be 196. All right. That concludes question number 2, a nice little prime factorization question. It certainly had the solution that we gave here had a little bit of extra information about prime factorizations and perfect squares and perfect cubes and perfect fourth powers that you might not have seen before. But that's okay. 2012 has passed. You're not writing this contest. These solutions will help you in the future on other contests if prime factorizations or perfect cubes come up. You can use the information you've learned here. And hopefully in most of the videos you glean a little extra information that helps in your future endeavors. And hopefully question number 3 will prove equally as informative. But we'll see that in the next video. So thank you so much for watching. I'll see you guys next time.